Okay, the next speaker is Sergei Sibiryakov, and his topic is black holes in ultraviolet-complete Horava gravity.
So this is a work that was done with in collaboration with Guillermo Lara, Mario Herrera-Valle, and Enrico Barause. And basically, it's a continuation of the study of UV complete model of gravity, which is called Horava gravity. Well, which is not precisely gravity, it's not precisely our general relativity, but it's a cousin of it. Okay, so let me move. Yeah, first let me motivate why we are considering this Horava gravity and what it is actually. Yeah. First, just look at GR, and we perfectly know that general relativity is not a complete theory. Yeah, so it has an ultraviolet cutoff of order of M Planck, and there are different ways to see it. But basically, like physically, we know that like scattering amplitudes, for example, of gravitons, they will grow with energy, or alternatively, we can argue that loop corrections grow with energy and become uncalculable. So one way to see it is to say, okay, let's just try to use perturbation theory. So we decompose the metric, substitute it into general relativistic action, Einstein action, and then we look at the free part first. And the free part is quadratic in the metric perturbations and quadratic in derivatives. And let us kind of zoom in on shorter scales. Yeah, so that we will do by scaling all coordinates by a certain like amount. And we want to understand how basically the characteristic scale of fluctuations of quantum fluctuations of the metric behave with this under zooming in. And we find basically the mathematical way to estimate this amplitude of fluctuations is to require that the action, quadratic action, is invariant under the scaling. Yeah, so we have to invent such a scaling of the metric so that this part of the action does not change. And we see that metric fluctuation scales in this way, which means that for any dimension, any space dimension bigger than 1, so any space-time dimension bigger than 2, actually the metric scales and grows when we go down to shorter scales, to shorter distances, which has an implication that the interaction terms, which contain further powers of the metric, they will grow when we scale down to small distances. So interactions grow on short scales and dominate at some point over the quadratic part, and we cannot use perturbation theory yet. Then we don't know what to do. Okay. So the idea to get around this problem was suggested by Piotr Horava, and it goes in the following way. So the first step is just to take the Einstein action and rewrite it in time-space split. Yes, so basically we do decomposition into time and space, and so far this is just Einstein action there. There is nothing new, just written in new variables where Kij is the extrinsic curvature of constant time slices. Essentially, it provides kinetic term for the metric, and here we have just curvature on the constant time slices, which provide a kind of potential, and I also include the cosmological constant here for future. So this action is, of course, yeah, though we have here the split in time and space, of course, it's invariant under full diffeomorphism group of arbitrary changes of time and of space and time, arbitrary changes of this foliation in constant time slices. And with this action, we already know it's not UV complete. So what we can try to do is the following, is to say, okay, let's deform this action in the following way. So we add, so basically we, I think the best way to formulate it is to say that we reduce the symmetry. So basically we renounce this arbitrariness of the choice of foliation, and that means that we physically, so now the foliation is physical, so it has its own degrees of freedom. So now the theory has reduced symmetry. Time can be just reparameterized as a function of itself, though the space coordinates can be still reparameterized arbitrarily. And this reduction of symmetry allows to write more terms in the action. Well, in particular, there will be one coupling which appears here in the kinetic part, which in general relativity was fixed to be 1. And moreover, we can add here in the kind of potential part, we can add additional terms with higher derivatives in space. So we don't add any higher derivatives in time because we don't want to have like more the second order equations of motion in time. But we can have higher derivatives in space. In principle, it's not forbidden, by quantum, by our dynamical requirements. Yeah, and like quantum mechanics can be constructed normally, and so on and so forth. So yeah. On the other hand, this allows us, this higher derivatives actually allow us to improve the convergence of quantum corrections or quantum fluctuations at short scales. So here now, the free part of the action, it will contain, like kinetic term, which is normal, quadratic in the fields and in time derivatives. And here in the space derivatives, it will be dominated by the highest, by the term with highest derivatives in this, Lagrangian L at the end, which I write here. So we write, by construction, we just put up to, like the highest order of derivatives we have here is 2 times d, where d is the number of space dimensions. And then when I want to kind of scale the free part of the action and in such a way that its form is preserved, I have to scale space and time differently. So, okay, space scales as before, but time scales with a different factor, which depends on this parameter, on this dimensionality d. And if I do the scaling, then I understand that I don't need to scale the metric at all. So metric fluctuations do not grow with distances, with shorter, do not grow at shorter scales, or otherwise we can say they don't grow at high energies. So basically now, this theory is analogous to, say, electrodynamics, where fluctuations do not grow at, well, actually they do grow at small distances, but they grow only perturbatively, logarithmically. So that's, at this point, we just reached, like the state analogous to QET. Actually, as I will argue in a second, there are, this theory, at least in some cases, more analogous even to QCD, where actually fluctuations become smaller at smaller distances. What else I want to say here? Once we reduce the symmetry, we have an option. We can put this function n, in the metric, basically this component of the metric, which is called laps, we can put it to be constant, to be 1. I mean, that's just reduction of dynamical configuration space of the theory, which is allowed by this reduced symmetry. Yes, so I think somebody hadn't switched off the microphone, so because I hear some sound, or there's a question. Okay. Okay. Is there a question? Okay. Shall I proceed? Okay, I will proceed then. Now, let's consider the simplest example of this theory, which is a theory in the space-time dimension 3. So we have 1 time and 2 space dimensions. So d is equal to. So in that case, the full action of the theory that is compatible with the symmetries that I described is this. So basically, we get apart from the coupling, which I said we had introduced before, this coupling lambda, we get another coupling mu, which multiplies square of the curvature. And I omitted the term linear in curvature here because in 2 dimensions, it's a total, it's a topological term. So its total derivative does not affect local dynamics. So let's list differences of this theory from general relativity. Okay, so differences are here. This lambda is not equal to 1, mu is not equal to 0, and that, as a result, like as a physical consequence, it has that the theory possesses a propagating degree of freedom, unlike 3-dimensional GR. And this propagating degree of freedom is scalar with the following dispersion relation. So omega squared is proportional to k to the 4. So it's an unusual quadratic dispersion relation. In some sense, at low moment, it becomes it stops being propagating. Yeah? And like second difference is that we set the lapse function to 1, and because of that we don't have any Hamiltonian constraint in this series. So yeah, so in this sense the dynamics of the series is quite, well, we can expect that it's quite different from general relativity, but we also expect that there should be something common because of this. After all, the series still has a very large symmetry, you know, like this time representation. Well, yeah, not time representation is not important, but what is important for me here that it has this space reparameterization, so it still has this large geometric symmetry in it. So we can expect that it may share some features with general relativity. But one thing which is actually distinct from general relativity is that this series is UV complete. So we calculated the RG flow, our renormalization group flow in this model, and what we find that, I mean, this renormalization group flow is shown here. So essentially, well, there are basically two couplings, lambda and kappa, gravitational coupling over square root of mu. These are two essential couplings of the theory, physical couplings. And you see, I mean, this flow shows like arrows, they show the direction of the flow from UV to IR. So meaning that UV will be here. And here we see, or here. And there are here the two fixed points. So one is at lambda equal 1/2 and 0 coupling. And another is at lambda equal 15/14 and 0 coupling, 0 gravitational coupling. Well, this fixed point here is a bit tricky because this is a boundary of physically acceptable values of lambda. Just, you know, inside this dashed region, the theory is not defined. It's not unitary. But this other, so this fixed point I will probably not discuss in this talk. But the other fixed point at lambda equal to 15/14 is perfectly fine. And moreover, maybe it's interesting that there are RG lines that flow from this point towards the value of lambda equal 1, which corresponds to general relativity. So there is, in the direction of the flow is in the right way, though the question whether the theory reduces to general relativity, and if yes, in what sense, is still open. You know, this limit when lambda goes to 1. Okay, so very good. So we got this nice quantum UV complete theory. What is it good for? So it's a bit like question of this sort. And of course, one thing which one wants to ask right away from any quantum theory of gravity is what happens with black holes, and with black hole paradoxes, information paradox, and all that. But here, actually, we stumble on a more basic question: are there any black holes in the theory at all? And that will be the main topic of my talk today. First, you may think that there are no black holes. It's just impossible to define anything like that because high energy modes, they propagate with arbitrary high velocity. Yeah. I didn't mention that, of course, the theory, because we break the symmetry or we put time and space on different footings, the theory does not feature Lorentz invariance in the ultraviolet. So because of that, the ultraviolet mode, they can propagate arbitrarily fast. Okay, there is no limit of the speed of light there. And that's, I mean, there will be no black hole then, one can say. And actually, that's just this statement is a bit premature as it is, because there is another version of the theory where n is not set to 1 when there are black holes, even for arbitrary fast propagating modes. But that's not what I'm gonna talk in this talk, because yeah, that requires to go to a different theory about which we don't know what its quantum properties are. We don't really know. In that case, it has not been yet fully analyzed. So in the model I'm focusing on, where n is set to 1, indeed, UV mode probe the whole space. Still, one can define some analogs of black holes starting from the low energies part of this theory. So I can imagine that there is some matter which propagates at low energies with normal speed of light. And if I have a metric that features horizon in the normal sense, like we are used to in GR, it will be, this horizon will be one-way surface, yeah, for these low energy modes. So perhaps high energy modes can propagate out, but low energy modes cannot propagate out. Yeah, they can only propagate in. Which means that, yeah, I can search for this type of objects, which look like black holes from low energy theory. Presumably, we can make them in the process of collapse of some long wavelength perturbations, and then we can still ask what happens with these objects and what their properties are. Okay, so to some extent I discussed already, but the idea is that we will be considering spherically symmetric metric ansatz, stationary. So that's the most general spherically symmetric ansatz. Well, actually, circular symmetric, where in 2+1 dimensions. This is parameterized by two functions: radial function g and shift function f, both functions of the radius. And if the shift function crosses 1 somewhere, that's actually the horizon in the normal sense we are all used to. So if we find a solution where this f crosses 1, this is horizon from low energy perspective. Yeah, a few comments here about, again, relation with general relativity. So we know that in 3 dimensions, in general relativity, there are no black holes if cosmological constant is non-negative. Yeah, for 0 or positive cosmological constant, there are no black holes. All solutions with, say, point sources, they just are conical defects. Yeah, so like point masses, they produce conical defects, and that's it. So there are no horizons formed. Of course, there are solutions. There are black holes in when lambda is negative in anti-de Sitter, so BTG black holes. But these are not good for our purposes, actually. Well, I mean, considering negative lambda is not good for us because anti-de Sitter space cannot be foliated, you know, by this constant time slices in such a way that lapse is equal to 1. That's basically impossible. So in other words, in this theory, there isn't, apparently, at least in the normal sense, there is no anti-de Sitter space. And not static anti-de Sitter, okay. Maybe there is some non-stationary analog of it. And that's why we cannot really go to the negative lambda case. So we'll focus on positive or 0 cosmological constant. Well, and then basically let's classify. So let's just sit down and calculate and classify all circular symmetric stationary solutions, taking this ansatz. Naively, we expect equations of motion to be of fourth order because we have fourth order terms in the action. In fact, after some massaging field definition, we can reduce field equations to a system of second order differential equations for variables f, function f, and function gamma, which is logarithmic derivative of the metric function, of the radial function. Well, still it's a coupled system of nonlinear second order differential equations, and it's not easy to solve, okay? So that's why let's analyze it in steps. So the first step is to consider low energy limit, or equivalently large distance limit, where we neglect terms with highest derivatives. So terms with which are multiplied by this parameter mu, we throw them away, basically setting mu to 0. So then the order of the system is reduced. So all this term goes away. That goes away. And derivatives. So basically, the order of the system is now reduced because the second equation, it now doesn't have any second derivatives. And then, yeah, the system can be solved. And that's the solution we get. So it's a general solution. We find like 2-parameter family of solutions parameterized by this, like letters, parameters B and G infinity. Here it's given in the parametric form. So it's given, like f, g, they're given as functions of x, and x itself, and the distance r is also given as a function of x. But okay, I don't expect you to to learn by heart this solution, just to say that it exists. Yeah, and it's not a general one. There are no other. Well, there are some other solutions, but they don't satisfy. They don't have reasonable asymptotics. Okay, so that's good moment to go to asymptotics. So what are asymptotics of this solution? So at large distances, f and g, they just reduce to the form written here. So f is a linear function of the radius, and g is just constant. And that's actually nothing but the Sitter spacetime, just written in this in a kind of well, in certain coordinates where basically lapse is set to 1. So it's just the Sitter with perhaps some deficit angle. So this g tilde, if it's different from 1, then there is an overall deficit angle in the Sitter. Okay, so these are reasonable asymptotic that we expect at infinity. But then let's look at closer to the center, and there these functions f and g, they reduce to power laws. The power laws, this one and this one, with the power law exponent sigma which depends on the coupling lambda. And if lambda is in the range between 1 and 15/14, okay, actually it can be even bigger, but okay, if it's not too big, then the sigma is positive, which means that radial function goes to 0. So that's what we expect, when we go to the center, maybe that's what normally would be expected. But this shift function grows. The shift function grows, and that implies two things. So one thing is that if I choose parameters of a solution in such a way that somewhere at the intermediate distances f is less than 1, then close to the center, it actually will cross this unit value. And that will correspond to a low energy horizon, as we discussed before. So this solution describes a low energy black hole. Of course, f crosses 1 also at large distances, but that's just the usual de Sitter horizon. Okay, so these are black holes from the low energy perspective. But the second thing that we see here is that divergence of this f signals singularity. Of course, so far we found just solution of low energy equation. So the next question to ask, what happens when we now include all higher derivative terms? And can it happen that these higher derivative terms resolve the central singularity? That would be nice, because then our solutions would be a kind of gravitational soliton, which would be regular everywhere, but still would have a low energy horizon, and we could study whatever we want. Could ask questions that we want to ask from black holes. We could address to these solutions. Okay, so next step is to include these terms proportional to mu. And this is a non-trivial, from a mathematical viewpoint, that's not a trivial step, because now we raise the order of the system of equations actually by 2. So we have more integration constants and have to do a kind of singular perturbation theory. But but also that can be considered at first. It can consider it as a bonus, that we have now more freedom, in our integration constants. So perhaps playing with these additional integration constants, we can smooth out the singularity. And just a priori, one can speculate what possible resolutions could be. One is that we get a regular center, but that's actually not the only option. Another option could be that we get an infinite extension of space-time to r towards r equal to -infinity, which would be, for example, we get another asymptotic region. So our space-time opens up in a new asymptotic region that would correspond to a wormhole. Or we could also, like generally, we can speculate that just this F and G remain bounded all the way up to infinite negative coordinate, which would correspond to a kind of throat. Yes, so that the black hole actually develops a throat inside. So to see if any of these possibilities is realized, we set up lambda equals 0, because lambda is responsible for large distance behavior. In the center, it should not matter. And look for solutions that have these power law asymptotics at large distances. Okay, so as I said, we're doing a kind of singular perturbation theory where we expand around the asymptotics, assuming the two functions to be small at large distances at least. And then the general solution for these perturbations F and G is given here. As expected, it has 4 parameters inside. And we can wonder if we can play with these parameters to get rid of the singularity. But first, of course, we have to satisfy the conditions, boundary conditions at infinity. So meaning that these functions should, well, not the function, but this perturbation should decay. And looking explicitly finding these solutions F3, G3, F4, G4, we actually found that they don't decay, none of them. They both oscillate with growing amplitude. So this part, these two solutions should be thrown out. Yes, so C3, C4 should be set to 1 just by conditions at infinity. Then we are still left with 2 parameters, C1, C2, and actually this perturbation decays. In particular, the C1 decays. Well, C2 does not decay, but okay, constant maybe still okay. But unfortunately, these 2 parameters, or maybe fortunately, I don't know, but they correspond to exact 0 modes of the solution. Because if we set lambda equal to 0, then the full system of nonlinear equations that I had on the previous slide, it actually features a symmetry, a 2-parameter symmetry of this type. So we can shift the coordinate r and we can rescale it. And one can check that these 2 modes precisely correspond to this type of transformations. And this type of transformation, of course, cannot remove the singularity. Yes, so if f diverges at some point, shifting it or rescaling it does not help. Yeah, just to make sure, we made a more detailed numerical analysis that indeed, shooting numerically, from various directions to make sure that no regular solutions exist. So basically, here we are with the summary. So we classified all stationary circular symmetric solutions in the UV-complete gravitational model by Horava without matter. Yeah, so we didn't include matter. And among those solutions, we find a whole family of what can be classified as black holes from low energy perspective. I put in quotation marks because they are not black holes for the full theory. And that is different from, of course, from 3-dimensional general relativity, where we didn't have any black holes. So these are good news. So bad news is that these solutions are singular. So all these black holes are singular. And from the point of UV theory, that's actually bad, because that corresponds to an H singularity. And at this point, I think we don't know if the solutions really have physical relevance or not. At least we cannot take them as they are, and we cannot analyze, we cannot address the questions we wanted to address. The questions about black holes that we wanted to address, we cannot do it at this moment using the solution because of this naked singularity. Perhaps to make a next step, the next step would be to include matter in the considerations and see if these solutions can be formed in processes involving matter. For example, if we can have like a solution, a kind of star that smoothes out the central singularity, and this metric that we found just describes the metric outside the matter distribution. And of course, like the most crucial question is whether the solutions can be formed in a kind of gravitational collapse, starting from smooth initial conditions. That would be ultimate answer whether the solutions have physical relevance or not. So that's all I have to say, and thank you for your attention.
Thank you for your talk. First question is from Nikita Kolganov.
Thank you, Sergei, for the nice talk. Today's talks on black hole information paradox probably teach us that UV incompletion of general relativity is not very important for such feature of black hole physics as black hole evaporation, but for what phenomena of black hole physics UV completeness of gravity theory is important from the perspective of your work?
Yes. So okay. So one feature is well, actually that work already has negative answer to it, so it doesn't work. So one feature could be that resolution of singularity. Yeah, decided that we believe that in general relativity, like central singularity, where density is very large, maybe not, resolved somehow by quantum effects. And so far in this model, we see that we don't get this resolution. So we have a theory where we control quantum effects and they are small. So then the resolution should have happened classically, but it has not. Yeah, so it's probably like fail at this moment. But as I say, perhaps we should make a next step and include matter and see how really like collapse happens and what happens during collapse. Second one is that even for information paradox, I think I tend to agree that it should mostly be answered by low energy physics, but there might be some caveats. Yeah, like yeah, actually, do we have remnants at the end of black hole evaporation or not? Maybe that's another question one can ask. And yeah, this kind of UV complete theory should be able to answer this question as well.
Okay, thank you.
Next question from Neil Turok. Neil, you should unmute your microphone. Unmute your microphone.
I just moved my screen, sorry.
Okay.
Yeah, thanks, Sergei, for a very nice talk. As far as I understood, the model has a scalar mode as well, right?
Yeah, that's right.
Okay, so it doesn't sound so hard to examine the question of if I have a collapsing scalar cloud, does it end up creating one of these singularities?
Yes, that's what we like envisage to do, though it's quite complicated technically. Well, one reason why we didn't do it yet, because the equations in space are higher derivative, yeah, in spatial derivative. So it's not normal hyperbolic system. It's kind of some kind of parabolic system, but also with not normal parabolic system, it's non-linear parabolic system. So yeah, so it looks quite challenging, though it's doable, certainly, yeah.
Okay.
Certainly doable.
Thank you.
Okay, next question, Alexander Zakharov.
Thank you very much. Do you hear me?
Yes.
Yeah.
If I understood you properly, first you found solution for mu vanishing value,
Yes.
and after that you consider solution for non-vanishing value. And
Yes.
that is, my question is, what about asymptotic behavior of your solutions for non-vanishing values? They converge to vanishing solution or not? And what about their behavior?
Yes, so they do. So once we set these perturbations to zero, they do converge. Yeah. Of course, the full system has more solutions. So they are parameterized, if you want, by these couplings, additional integration constant C3, C4. Once we set C3, C4 to zero, then our full solutions converge to well, converge everywhere away from the singularity. The behavior at the singularity is different. But
Yes.
yeah, at finite distances, they converge to original solutions. Yeah.
Okay, thank you.
Well, we will have two more questions. Next is from Alexander Wickman.
Hi, Sergei, thanks a lot. Very, very nice talk. By the way, but as far as I understand, your singularity is not end of time singularity because of the structure of the model, right? It's like really point-like singularity. It's like a point in the space, right?
Yes, it's like really like literally center, which is singular, yeah, with infinite curvature in there. Yeah. So time-like naked singularity.
Right. So basically, of course, it can be only time-like if it's naked, right? I think.
Yeah.
Just geometrically. So, but it would actually imply some instability from the point of view of low energy theory, right? Like all these Cauchy horizons are usually unstable.
Well, yeah, I don't know if it applies instability per se. So I would say no. I would say this solution should not form. Yeah. Well, so maybe what should happen perhaps if I really consider like collapse of something, of some matter, or maybe the scalar gravitons, they could perhaps bounce, away from the singularity. That would be interesting resolution. Or they could form a star somehow, yeah, if some part of it is radiated and maybe some other like part of matter forms a star where the singularity is smoothed out. Also another possible scenario. And finally, of course, there is a scenario when really like things collapse and form the singularity. And that would be, yeah, then I would not know what to do, actually, to say. Maybe it would be a pathology theory that should thrown away.
Right. By the way, do you also know anything what happens if you try to generalize it to proper 4D? So, I mean, 3+1?
Well, 3+1, we first want to understand UV properties, yeah? So in a sense, yeah, there are some kind of pieces of knowledge about 4D, but I think we want first to make sure that it has this UV asymptotic freedom property, if it does or not, and then go to black hole, because, yeah, if we're considering something which is not well-defined quantum mechanical, then it's not interesting. Then it's like GR. But GR is better.
Okay,
Great,
the last
great,
question.
thanks.
The last question from Andrei Shkerin.
Yeah, actually, I had a very similar question. So, what can you say about classical stability of these black holes?
These black holes. Yeah, but for these solutions, I don't think I even know how to pose this like stability question because of this naked singularity. You have to postulate some boundary conditions on the naked singularity, and perhaps the answer will depend on that. So, but yeah, at this point, yeah, we haven't tried to play with this this game.
Okay, I think we are done. So I'd like to close the session, and I would like to thank all speakers for very interesting talks.